Chemistry of water treatment. The standards to drinking water vary according to type and size of water system. So community water system is one that serves the same people year-round. Examples include those in cities and small towns that provide water to residences, homes, condominiums, and mobile home parks. Then the non-community water system serves the public but does not serve the same people on a year-round basis. Non-transient non-community water system is defined as one which serves the same people for 6 months but not year-round. While the transient non-community water system is the opposite, because it serves the public but do not serve the same individuals for more than 6 months. So rest areas and campgrounds are considered as transient non-community water system. Drinking water standards are classified either primary or secondary. The primary drinking water standards are established to ensure safe, finished water, include microbiological organisms, disinfection, byproducts, organic chemicals, many of which are priority pollutants in organic chemicals, radionuclides, and turbidity. Then the secondary drinking water standards. So these standards are not related to health and are therefore non-enforceable by the US EPA. So the secondary contaminants cause a variety of problems that can be categorized as aesthetic, cosmetic, and technical effects. They relate to the aesthetic of the water, making it more desirable to the consumer. So other rules promulgated by the EPA. The groundwater rule. Its purpose is to reduce disease incidence associated with microbial contaminants in drinking water, and it applies to all systems that use groundwater as a source of drinking water. Then long-term 2 enhanced surface water treatment rule. The LT2 rule is to reduce illness linked with the contaminant cryptosporidium and other disease-causing microorganisms. Then stage 2 disinfectants and disinfection by products rule focuses on public health protection by limiting exposure to disinfection by products, especially total trihalomethanes and 5-haloacetic acids. Long-term 1 enhanced surface water treatment rule. The purposes of this rule are to improve the control of microbial pathogens in drinking water, especially the protozoan cryptosporidium, and address risk trade-offs with disinfection by products. Filter backwash recycling rule. A rule governing the process of recycling wastewater from the backwashing of drinking water filters. A method of reducing potential risk to consumers from microbial contaminants. Then the arsenic rule. The rule requires monitoring for new systems and new drinking water sources, and also clarifies the procedures for compliance with MCLs established for inorganic contaminants, synthetic organic chemicals, and volatile organic chemicals. Lead and copper rule. On June 7, 1992, US EPA published a regulation to control lead and copper in drinking water. The rule requires all community water systems and non-transient non-community water systems to comply with the rule. Total coliform rule. The rule establishes both MCLGs and MCLs for the presence of total coliform in drinking water. All public water systems must monitor for the presence of total coliforms in the distribution system at a frequency proportional to the number of people served. Stage 1 disinfectants and disinfection by products rule. It improves drinking quality by providing protection from disinfection by products. Interim enhanced surface water treatment rule. This improves the control of microbial contaminants, particularly cryptosporidium, in drinking water systems serving 10,000 persons or more, and that use surface or groundwater under the direct influence of surface water. Surface water treatment rule. It seeks to prevent waterborne diseases caused by viruses Legionella and Giardia lamblia. The rule requires public water systems that use surface water sources and groundwater sources under the direct influence of surface water to filter and disinfect the water. Overview of typical processes used for contaminant removal. So this is the list of parameters and the processes used for the removal. Coagulation. So, coagulation is a method used to alter the colloids so that they will be able to approach and adhere to each other to form larger flux particles. In other words, it is used to turn the small particles of color, turbidity, and bacteria into larger flux, either as precipitates or suspended solids. Colloid destabilization. Colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize this charge. Such neutralization can take place by the addition of an ion of opposite charge to the colloid. Since most colloids found in water are negatively charged, the addition of sodium ions should reduce the charge. Key components of coagulant. First, the trivalent cation. As indicated in the last section, the colloids most commonly found in natural waters are negatively charged. Hence, a cation is required to neutralize the charge. A trivalent cation is the most efficient cation. Non-toxic. This requirement is obvious for the production of safe water. Moreover, the coagulant should be insoluble in the neutral pH range. The coagulant that is added must precipitate out of solution so that high concentrations of the ion are not left in the water. Such precipitation greatly assists the colloid removal process. So these are the most commonly used coagulants. Aluminum sulfate. When alum is added to the water, this reaction occurs. If the second reaction occurs, lime or sodium carbonate may be added to neutralize the acid. When aluminum is added to the water, it immediately dissociates, forming complex products that coagulate. It produces very large precipitates that catches the colloids as it falls to the water. The precipitates are called flux. Flux formation is one of the most important properties of a coagulant for efficient colloid removal. The coagulation process by aluminum is done by absorption and charge neutralization and sweep flocculation. Ferrous sulfate. Oxygen is required for oxidizing the ferrous ion to ferric, since ferrous hydroxide is soluble. The pH must be raised to approximately 9.5 so that the ferric ions are precipitated as ferric hydroxide. Ferric sulfate. Dense, rapid settling flux are produced, and the optimum pH range for the ferric sulfate is from 4 to 12. Ferric chloride. Dense, rapidly settling flux is produced when ferric chloride is used as the primary coagulant. Ferric chloride reacts with the natural alkalinity. Coagulant aids. pH adjusters. It comprises acids and alkali, used to adjust the pH of water in the optimum level during coagulation. Acid that is commonly used to lower the pH is sulfuric acid, while the base commonly used to raise the pH are either lime or soda ash. Activated silica. The addition of activated silica is especially useful for treating highly colored, low turbidity waters because it adds weight to the flux. However, activation of silica does require proper equipment and close operational control, and many plants are hesitant to use it. Clay. It acts just like activated silica, adds weight to the flux but with slightly negative ions, useful for colored, low turbidity water, but clay is not commonly used. Polymers are long-chain carbon compounds of high molecular weight that have many active sites, can be anionic, cationic, or non-ionic. The active sites adhere to flux, joining them together and producing a larger, tougher flux that settles better. This process is called interparticle bridging. Softening. Softening is a removal of polyvalent cations from water that cause hardness. The hardness in water is primarily attributed to the divalent metallic cations like calcium ions and magnesium ions. There are two softening methods, boiling and chemical precipitation. Boiling is the simplest. It removes temporary hardness due to calcium and calcium carbonate, while chemical precipitation is used for the removal of permanent hardness by adding lime and soda. The hard water does not lather with soap solution and forms white curd like precipitate or scum. The total hardness is the sum of calcium ions and magnesium ions. So two types of hardness, the carbonate hardness and the non-carbonate hardness. The carbonate hardness is associated with carbonate and bicarbonate anions. It is only temporary hardness and can be removed by boiling or by addition of lime. While the non-carbonate hardness is a permanent hardness and can only be removed by chemical precipitation. Conditions. So if alkalinity is lesser than the total hardness, then the carbonate hardness is equal to alkalinity. But if alkalinity is greater than or equal to total hardness, then the carbonate hardness is equal to the total hardness, and the non-carbonate hardness is 0. The non-carbonate hardness is the difference between total hardness and carbonate hardness. Chemical precipitation. It is accomplished by adding lime and soda ash to water. If magnesium ion concentration is less than 40 mg per L as calcium carbonate, and the non-carbonate hardness is not present, then soda ash may not be used. The dissolution reactions and solubility expression for calcium carbonate and magnesium hydride at 25 degrees Celsius. When the product of the calcium ion concentration and the carbon ion concentration exceeds the solubility product of calcium carbonate will be precipitated from solution, resulting in a lower calcium ion concentration. The practical solubility limit of calcium carbonate is approximately lime soda softening. The objective is to precipitate the calcium as calcium carbonate and magnesium as magnesium hydroxide by raising the pH to 10.3 and 11 respectively. The calcium carbonate is found by converting the bicarbonate present into a carbonate and adding calcium. So, magnesium hydroxide is formed by adding hydroxyl ions. So, hydroxyl ions are found in calcium hydride, which is found in hydrated lime. If hydrated lime is not available, quicklime is used to form hydrated lime. Quicklime is added to the water and the process is called slaking. So, the softening reactions. The neutralization of carbonic acid, precipitation of carbonate hardness due to calcium, precipitation of carbonate hardness due to magnesium, removal of non-carbonate hardness due to magnesium, removal of non-carbonate hardness due to calcium. Single-stage softening or selective calcium removal can be used on waters with a magnesium concentration less than 40 mg per liter as calcium carbonate. First stage treatment consists of flash mixing of lime, followed by flocculation, sedimentation, recarbonation, and filtration. Flocculator or clarifiers or solids contact units are often used in place of conventional coagulation, flocculation, and sedimentation. Lime is added in the first stage to meet the stoichiometric requirements for the neutralization of carbon dioxide, if present, and calcium carbonate hardness precipitation as calcium carbonate. An excess dosage of lime, typically 1.25 MEq per liter, is added above stoichiometric amounts to raise the pH above 11 for the precipitation of magnesium as magnesium hydroxide. The second stage treatment involves flash mixing of soda ash, followed by flocculation, sedimentation, recarbonation, and filtration. Soda ash is added to the water for removing calcium non-carbonate hardness. Softening using the split treatment scheme involves treating a portion of the raw water by excess lime treatment. then blending this softened water with remaining portion of raw water by pass. The ratio of the bypass flow to treated flow is determined using the following. So other softening method is the ion exchange process. Mixing and flocculation. The process whereby the chemicals are quickly and uniformly dispersed in the water is called mixing or rapid mixing. The degree of mixing is measured by the velocity gradient, G. G is the function of the power input into a unit volume of water. If the value of gradient conditions, if the value of the if the value of velocity gradient is high and time t is low, the flux are small and denser. If the value of G is low and the T is high, flux are larger. If the value of G is low and T is high, flux are large. So rapid mix, probably the most important physical operation affecting coagulant dose efficiency. Rapid mixing can be accomplished within a tank utilizing a vertical shaft mixer, within a pipe using an inline blender, or in a pipe using static mixer. Other methods such as partial flumes, hydraulic jumps, baffled channels, or air mixing may also be used. So rapid mixing tanks, the rapid flow impeller provides more turbulence and is preferred. Rapid mixing tanks, rapid mixing tanks, the radial flow impeller provides more turbulence and is preferred for rapid mixing. Flocculation, the contacting process of precipitates formed during coagulation and softening to form larger particles called flocks and is done by slow, gentle mixing. Primary types of devices used in water treatment: paddle wheel flocculators and vertical turbine mixers. Paddle wheel flocculators may use horizontal or vertical shaft, but typically horizontal shafts are preferred at conventional water treatment plants. In recommended standards for waterworks, engineers are encouraged to use tapered flocculation to produce large, dense floc. Tapered flocculation, employing 3 separate compartments, each at a different velocity gradient, is normally practiced so that a dense, good settling floc is produced. Typical G values used in the first, second, and third compartments respectively are 50, 20, and 10 seconds raised to the power of -1. The velocity gradient varies from 10 to 100 seconds raised to the power of -1, and the GR parameter varies from 104 to 105. The power dissipated in the water by a paddle wheel flocculator is calculated using the following equation. Normally, 0.70 to 0.80 of the paddle velocity vertical shaft turbine flocculators. In new water treatment plants and those that use direct filtration, vertical shaft turbine flocculators are typically used. This type of flocculator has an impeller attached to a vertical shaft that is rotated by an electric motor. There are different types of impellers that produce either radial or axial flow mixing. Important design parameters for these types of flocculators include power number, effective tank diameter, and diameter to effective tank diameter ratio. The power number is calculated using the following equation. Sedimentation. Sedimentation is a physical water treatment process using gravity to remove suspended solids from water. gravity settling or sedimentation, is considered as a major unit operation involving solid-liquid separation using gravitation force. Discrete settling occurs in grid chambers at wastewater treatment facilities and can be analyzed by calculating the settling velocity of the individual particles contained within the water. The three forces that act on particles as it settles: gravitational force, buoyant force, and drag force. Free settling is observed when there are discrete non-flocculent particles whose size, shape, and specific gravity do not change with time as they settle. Particles settle as individual entities and there is no interaction between particles. Terminal settling velocity: the velocity reacted by particle as it falls through a fluid dependent on its size, shape, and the difference between its specific gravity and that of settling medium, used to sort particles by grain size. For spherical particles, the volume and cross-sectional area are calculated using the following equation. Settling velocity equation. Flocculation settling occurs in primary clarifiers and during settling of coagulated water and wastewater. As flocculent particles settle, their size, shape, and density and settling velocity will change with time. Percent removal of suspended solids is then plotted as a function of depth and time. Percent removal is calculated using equation 6.96. Flocculent settling laboratory procedure. Flocculent settling column analysis are typically performed in a clear PVC column with sampling ports spaced approximately 6 inches apart. A column in the order of 5 to... Ay, puta, putang ina. Flocculent settling laboratory procedure. Flocculent settling column analysis are typically performed in a clear PVC column with sampling ports placed approximately 6 inches apart and a column on the order of 5 to 6 feet is used. So this is the procedure. Ideal settling basin. Overflow rate serves as a design parameter used by engineers to determine the size of settling basins, whereas water treatment plant operators regulate the flow through the basin to maintain the proper detention time and overflow rate to achieve optimum solids removal. The overflow rate is a different way of expressing the settling velocity of a particle as calculated using Stokes' law. Remember, settling velocity is a function of the diameter of the particle. Theoretically, all particles with a diameter equal to or greater than the particle size as specified by overflow rate should completely remove. The basis for design of a settling basin is to select a specific diameter particle that will settle by gravity during time that it takes water to travel through the basin. Under ideal conditions, a particle will travel a vertical distance of h during t. Mathematically, the distance traveled is equal to the rate multiplied by time. Detention time or retention time. It is defined as the time that the water remains in the settling basin. The wire loading rate, Q, is defined as the volumetric flow rate divided by the length of the influent wire. The wire loading rate is defined as the volumetric flow rate divided by the length of the effluent wire. Regulatory agencies sometimes specify wire loading rates that must be maintained in settling basins. The settling basin design criteria. The settling basin design criteria are the following. The settling basin design criteria are the following. Criteria. Settling basin design criteria are the following. Filtration. Filtration is a process for separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Water fills the pores between the sand particles and the impurities are left behind, either clogged in the open space or attached to the sand itself. At most water treatment plants, granular media filters are used. However, membrane processes including microfiltration and ultrafiltration are now being used. Filter classification. Numerous ways of classifying filters. Degravity filters, filters that are operated using gravity flow and operate a downflow mode. Filtration rate is the flow rate applied to the filter divided by the surface area of the filler bed. Then slow sand filters, rapid sand filters, and high rate filters or pressure filter. The last classification method is based on the type of media used in filter. The single media or monomedia filters only one type of the media, typically sand or crushed anthracite coal. Dual media filters are normally consist of a layer of a coarse anthracite above a layer of a sand. Then multimedia filters such as trimedia filters that consist of a top layer of anthracite coal, middle layer of sand, and a bottom layer of ilmenite or garnet. Suspended solids removal mechanisms, filter media. The effective size and uniformity coefficient. Effective size determined from the sieve analysis curve and represents the media for which 10% by weight of grains are smaller. Uniformity coefficient, a measure of size range from the media, and is defined as the ratio of D10 over D60 sizes that are determined from the sieve analysis curve. Properties of filter media. The effective size, uniformity, coefficient, depth of media, and depth. The effective size, uniformity, coefficient, depth of media, and depth of media to effective size ratios for various type of filter media are presented in the table. Granular media filtration. Primary goal is to use the entire filter bed for solid removal rather than being strained at the surface. The Darcy-Weisbach equation. Karman-Kozeny equation for head loss across a clean filter bed. Karman-Kozeny equation for head loss across a clean filter bed used to calculate friction factor F. Rose equations. Equations used to calculate the drag coefficient. The Ergun equation, the most widely used empirical equation for estimating head loss in clean granular media filter. Backwashing of filters. Periodically, granular media filters must be backwashed to remove particulates and turbidity that build up during the filter run. Operators backwash a filter based on one of the following scenarios. A. When the head loss through the filter reaches 8.10 feet. B. When the turbidity in the effluent reaches a specific levels such as 0.20 NTU, and when the filters has been in operation for a specified amount of time, for example, 24 to 96 hours. Backwash hydraulics. During backwashing, the water flow through the filter bed is reversed, thus expanding and fluidizing the bed. The porosity of the expanded bed could be estimated using this equation. Filter arrangement. Filters are typically placed adjacent to one another along one or both sides of a pipe, gallery, or gullet. Rapid sun filters are usually rectangular in shape with an average length, width ratio about 1 to 25 and surface area ranging from 450 to 4,500 feet squared. Conventional gravity filters use length to width ratios of 2 to 2 and 4 to 4 to 1. Surface area of gravity filters typically range from 250 to 1,000 feet squared, and filter depths range from 12 to 20 feet. Filter arrangement. The equation for the total number of filters. For water treatment plants processing lesser than 2.0 mgd, a minimum of 2 filters should be used. For large water treatment plants processing over 20 mgd, filters are composed of 2 cells per filter with a gullet running down the center. Disinfection. So, disinfection practice at water treatment plants has Disinfection. So, disinfection practice at water treatment plant has traditionally been the use of chlorine gas as the primary means of killing pathogens in water. The goal of disinfection is to inactivate pathogenic organisms such as bacteria, protozoa, and enteric virus that may be present in water. So, these are the major disinfectants in water industry. Chlorine dioxide. It is a powerful oxidizing agent that has been used primarily to remedy taste and odor problems in drinking water. Chlorine dioxide must be generated on site by mixing solutions of aqueous chlorine with sodium chloride as shown below. These are the advantages of using chlorine dioxide. However, there are disadvantages. Ozone, one of the strongest oxidants and disinfectants available. It is an allotropic form of oxygen that must be generated on site, typically by passing clean dry air or oxygen through a high-strength electrical field. The advantages of using ozone. The disadvantages. Ultraviolet radiation or UV generated by mercury vapor arc lungs in a non-chemical means of disinfection. UV radiation in the range of 245 to 285 nm is effective against bacteria and viruses. UV lamps are placed inside of quartz leaves which are then placed into the water. So the advantages of using UV. The disadvantages. Adsorption. So, adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. So, adsorption may be classified as physical absorption or chemical absorption. The physical absorption is due to van der Waals forces. It has weak bonding and reversible. The chemical adsorption is due to chemical bonding by reaction and usually irreversible. Both classifications are exothermic. So absorbents used in water treatment. The most commonly used is the activated carbon. But there are other existing adsorbents. The natural or synthetic zeolites, natural clay minerals, silica gel or activated aluminum or silicic acid. Activated carbon, the most commonly used adsorbent and is particularly suited to the removal of refractory organics. So there are two types, the powdered activated carbon or PAC and granulated activated carbon or GAC. The PAC is fed to the raw water in a slurry or powder and is generally used to remove taste and odor-causing substances or to provide some removal of synthetic organic chemicals. While the GAC is added to the existing filter system by replacing the anthracite with GAC, or an additional contractor is built and is placed in the flow scheme after primary filtration. GAC has proposed to be used to remove naturally occurring organic matter. GAC will typically last only for 90 to 120 days until it loses its adsorbent capacity, hence it is regenerated. The effectiveness of using the activated carbon. Membranes. A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the membrane process, the feed stream is divided into two streams, the concentrate or the reject stream, and the permit or product stream as shown in the figure below. The membrane is at the heart of every membrane process and can be considered as a barrier between the feed and the product water that does not allow water contaminants to pass as represented. There is a pressure drop across the membrane, called the transmembrane pressure or TMP, that must be overcome by the water feed pump. The performance or efficiency of a given membrane is determined by its selectivity and the applied flow. The efficiency is called the flux and is defined as the volume flowing through the membrane per unit area and time. The selectivity of a membrane toward a mixture is expressed by its retention and is given by membrane can be described by a variety of criteria including membrane pore size, molecular weight cutoff, membrane material and geometry, targeted materials to be removed, type of water quality to be treated, and/or treated water quality. So along with these criteria, membrane processes can also be categorized broadly into pressure-driven and electrically driven processes. First, osmosis. This process has traditionally been employed for the removal of salts from brackish water and seawater. It depends upon applying high pressure across the membrane in order to overcome the osmotic pressure differential between the saline feed and the product waters. Nanofiltration. This process, also called membrane softening, lies between RO and ultrafiltration. This membrane process employs 500 to 1000 kPa for operation. Ultrafiltration. The UF membranes cover a wide range of molecular weight cutoffs and pore sizes. Operational pressure range from 70 to 700 kPa depending on the application. Then the microfiltration. A major difference between MF and loose UF is membrane pore size. The pores of MF are approximately an order of magnitude greater than those of UF. The primary application for this membrane process is particulate and microbial removal. The hierarchy of pressure-driven membrane processes. Internal construction of spiral wound reverse osmosis membrane.